Beyond LLMs, the next breakthrough technologies that will disrupt AI. For the last 2 years, the AI story has been dominated by one thing: the large language model, chatbot, co-pilots, prompting, text generation. And that made sense. LLMs changed how millions of people work. But if you only watch the LLM layer, you can miss what is happening underneath it. Because the next phase of AI is not just about making language models bigger. It is about giving AI new senses, new memory, new ways to act, new ways to learn privately, new ways to understand the physical world, and in some cases, new ways to do science that humans simply could not do at the same speed. In other words, the next breakthroughs are not just better chatbots. They are new technical architectures and product categories that move AI from talking about the world to operating inside it. And there is already real-world evidence that this shift is underway. Google introduced Gemini as a multimodal model family and Project Astra as a prototype for a universal assistant, then began bringing Astra-style live multimodal capabilities into products. Google also says Lens is now used by more than 1.5 billion people each month, which is a huge signal that visual AI is already mainstream, not experimental. Anthropic and OpenAI have both released computer use systems that can operate interfaces. Apple has made on-device AI and private cloud compute central to Apple Intelligence. Google research has shown real production deployments of federated learning in Gboard. DeepMind's AlphaFold systems have already changed biology, and AlphaGeometry plus AlphaProof showed that hybrid reasoning systems can solve Olympiad-level math at metal standard. So, in this video, we are going beyond LLMs. We are looking at the next technologies that are already showing evidence of disruption. Multimodal systems, computer-using agents, world models and physical AI, small on-device AI, privacy-preserving learning, AI for science, neurosymbolic reasoning, and finally, the engineering bottlenecks that may force the next architectural leap. Because the next chapter of AI will not be defined by text alone. It will be defined by systems that can see, act, simulate, verify, discover, and eventually escape the limits of the current hardware stack. Section 1. Multimodal AI. When models stop being text-only. The first breakthrough beyond classic LLMs is multimodal AI. This is not a small upgrade. It is a change in what the model is. A text-only model predicts words. A multimodal system can process combinations of text, images, audio, video, and in some cases live sensor input. That matters because the real world is not made of text prompts. The real world is visual, spatial, auditory, and dynamic. And once a model can interpret those signals together, it becomes useful in situations where chatbots are too limited. Google made this shift explicit when it introduced Gemini as built to be multimodal. Then it pushed that idea further with Project Astra, a research prototype designed as a universal AI assistant that can understand the world around you in real time. Google later brought Astra-style live capabilities into Gemini and Search. That is disruptive because a system that can watch, listen, and respond in context no longer needs the user to describe everything in words first. And there is already mass-market proof that this matters. Google says Lens is used by over 1.5 billion people per month. That means visual search is no longer a niche feature for early adopters. It is already a global habit. That is a real sign that AI is moving from text interfaces into camera-led interfaces. Think about what that means in plain English. A normal chatbot waits for you to explain a problem. A multimodal system can inspect the problem itself. That changes the value proposition. In business, that means visual inspection, document review, warehouse monitoring, equipment support, field assistance, and medical image support all become more realistic. In consumer products, it means assistants that can look at what you are looking at and help in the moment. The disruption here is not just that the model can see an image. The disruption is that it can connect what it sees to language, memory, search, reasoning, and tools. That is the difference between a chatbot and an assistant with perception. Section 2. Computer using agents. AI that can actually do the work. The second breakthrough is computer using agents. This is where AI starts moving from advice to execution. For years, most AI systems had a simple limitation. They could generate outputs, but they could not reliably operate the software environment where actual work happens. That is now changing. Anthropic's computer use tool allows Claude to inspect screenshots, move a mouse, type on a keyboard, and interact with computer environments autonomously. OpenAI introduced Operator as a research preview of an agent that can use its own browser to perform tasks. And OpenAI says its computer-using agent combines vision with advanced reasoning to operate software through graphical interfaces like a human user would. This is disruptive because most digital work still happens inside software that was built for humans. Not for APIs, not for agents, for humans. That means a huge amount of work still lives inside websites, spreadsheets, admin portals, forms, dashboards, support tools, browser tabs, and legacy enterprise software. If AI can use those interfaces the way people do, then automation stops being limited to whatever has a clean integration. It expands to the long tail of digital work. And the performance is improving fast enough to matter. Anthropic's Sonnet 4.6 system card says the model achieved a 72.5% OS World Verified score, which Anthropic describes as near the frontier on benchmarked computer use tasks in a live Ubuntu environment. That is not proof the problem is solved, but it is strong evidence that machine control of real software is getting practical. There is also another layer that makes this more disruptive. Agents need access not only to interfaces, but to tools and data. That is where protocols matter. Anthropic introduced the Model Context Protocol, or MCP, as an open standard for connecting AI applications to external systems, including files, databases, search tools, and workflows. In simple terms, it is a standardized way for AI systems to reach into the software and data stack around them. That matters because standards remove friction. And when friction falls, ecosystems scale faster. So the real breakthrough is not just an AI that clicks buttons. It is the emergence of an agent stack. Vision, reasoning, tool use, software control, and standard ways to connect to external data. That is how AI moves from co-pilots to workers. Section 3. World Models and Physical AI, from predicting text to simulating reality. The third breakthrough is world models. A language model predicts tokens. A world model tries to predict how an environment evolves. That may sound abstract, but it has major consequences. If an AI system can simulate a world, it can train agents, test decisions, generate edge cases, and learn physical behavior without always needing expensive real-world trials. Google DeepMind described Genie 2 as a large-scale foundation world model that can generate diverse, interactive 3D environments for embodied agent research. DeepMind later pushed the category further with Genie 3, which it describes as a general-purpose world model that can generate photorealistic, interactive environments from text. NVIDIA is pushing the same direction from the robotics side. The company introduced Cosmos as a platform of world foundation models for physical AI, including robots and autonomous vehicles, and said early adopters include 1X, Agility Robotics, Figure AI, and Skilled AI. NVIDIA also introduced GR00TN1 as an open humanoid robot foundation model trained on human video, real and simulated robot trajectories, and synthetic data. Why is that disruptive?
Industrial enterprises use
Because one of the
physical
biggest
AI
bottlenecks
to
in
automate
robotics
physical
and
work.
autonomy is data.
Physical AI
Real-world
embodies
robot
robots
data
like
is slow
self-driving
and expensive
cars
to
that
collect.
safely navigate the
And
real
in
world.
many cases, it is
Manipulators
risky.
that perform
You cannot
complex
crash test
industrial
everything
tasks.
in the real world
And
forever.
humanoid robots
You cannot
who work
expose physical
collaboratively
robots to every
alongside us.
edge case you care about.
Plants and
World
factories
models
will be
change
embodied
that.
by physical AI,
They let you generate
capable
training
of monitoring
environments,
and
edge
adjusting its
cases,
operations,
and
or
scenarios
speaking to
synthetically.
us.
So instead
NVIDIA
of teaching a
builds three
robot only
computers
from the
to
world as
enable
it is,
developers to
you can
create
teach it
physical
from
AI.
worlds you can generate.
The models are first
That
trained on
changes the
DGX.
economics of physical
Then,
AI.
the AI is fine-tuned
And once the
and
economics
tested
change,
using
the
reinforcement
pace of
learning
iteration
physics
changes.
feedback in Omniverse.
That matters because
and the
in
trained
technology,
AI runs on
faster
NVIDIA
iteration
Jetson
often matters
AGX
more than raw
robotics
brilliance.
computers.
A system that can learn
NVIDIA
from 10,000
Omniverse is a
scenarios
physics-based
overnight
operating
will
system
usually
for physical
outpace a
AI
system that learns
simulation.
from 10 real-world
Robots
trials
learn
a
and
week.
fine-tune their skills
That is
in
why
Isaac
world
Lab,
models matter.
a robot gym built
They
on
are
Omniverse.
not just video tricks.
This is
They are the bridge between foundation models and physical systems. Section 4. Small, on-device, and private AI. The shift from cloud-only to edge intelligence. The fourth breakthrough is small and on-device AI. This matters because the LLM era trained people to think that more intelligence always means larger models in larger data centers. But there is another direction. Smaller models that are cheap, fast, local, and private. Microsoft's Phi line is a clear example. Microsoft describes Phi 4 as a 14 billion parameter small language model that delivers high-quality results at a small size. Microsoft has also said Phi reasoning models show how carefully curated data can let small models compete with much larger systems on complex tasks. Apple is taking a parallel path. Apple says Apple Intelligence combines on-device models with private cloud compute, and its developer materials say apps can use models on-device or through private cloud compute when needed. Apple also says the Foundation Models framework gives developers direct access to the on-device model, and its materials describe private cloud compute as extending the privacy and security of the device into the cloud. This is disruptive for several reasons. First, latency. If a model runs locally, the experience can feel immediate. Second, privacy. Sensitive data does not always need to leave the device. Third, cost. Not every AI task deserves a frontier-scale cloud model. And fourth, distribution. Once AI runs on consumer devices, the installed base becomes the platform. That is a very different business model from cloud-only AI. In the cloud-first world, AI adoption is gated by API costs and server capacity. In the on-device world, AI becomes a built-in feature of hardware ecosystems. That can spread much faster. And this is why small model efficiency matters so much. The future probably does not belong to one giant model doing everything. It looks more like a tiered stack. Tiny models on device. Mid-sized models at the edge. Larger models in privacy-aware cloud environments. And frontier systems for the hardest tasks. That layered architecture is likely to be more durable than the fantasy of one model to rule them all. Section 5. Privacy-preserving learning. AI that improves without collecting everything. The fifth breakthrough is privacy-preserving learning. This gets less attention than flashy demos, but it may become one of the most important infrastructure changes in AI. The classic AI bargain has been simple. Give the system more centralized data, and it gets better. But that bargain is running into legal, ethical, and practical limits. Companies and users do not always want sensitive data sent to a central server. So the technical question becomes, can you improve models without moving raw data? Federated learning is one of the strongest real-world answers we have. Google Research has spent years deploying it in Gboard. Google's earlier published work on mobile keyboard prediction said the system demonstrated the feasibility and benefit of training language models on client devices without exporting sensitive user data to servers. More recent Google Research work says Gboard's on-device language models now benefit from private training, and that years of work in federated learning and differential privacy power those production systems. That is disruptive because it changes the data architecture of AI systems. Instead of shipping raw data to the model, parts of the learning process move toward the data. For healthcare, finance, government, and consumer devices, that can be the difference between a deployable AI system and one that never gets approved. And Gboard matters because it is not a toy example. It is a global consumer product used at real scale. Google research also says federated learning enables mobile devices to collaboratively train shared models while keeping training data on the device, and later work added formal differential privacy guarantees to that setup. Why does this matter for the future of AI? Because the next decade will not be defined only by who has the biggest model. It will also be defined by who can build AI systems that organizations are actually willing and allowed to use. In many industries, privacy-preserving architectures are not optional. They are the price of entry. This is one of those quiet shifts that looks technical until you realize it changes deployment economics everywhere. Section 6. AI for science and biology. When models stop summarizing papers and start changing discovery itself. The sixth breakthrough is AI for science. This is where the conversation gets much bigger than productivity. Because once AI starts improving the rate of scientific discovery, it stops being just a software category. It becomes a research instrument. AlphaFold is the clearest example. DeepMind says AlphaFold has revealed millions of intricate 3D protein structures, and the AlphaFold protein structure database now provides more than 200 million protein structure predictions. DeepMind also says experimental structure determination can take years and cost hundreds of thousands of dollars for a single protein. That alone is disruptive. But AlphaFold 3 went further. DeepMind says AlphaFold 3 predicts the structure and interactions of all life's molecules, including proteins, DNA, RNA, and ligands. That matters because drugs are often small molecules interacting with biological targets. If a model gets much better at predicting those interactions, it can change drug discovery workflows directly. And there is commercial evidence that this matters. Isomorphic Labs announced strategic collaborations with Eli Lilly and Novartis that it said could be worth nearly $3 billion, excluding royalties from future drug sales. It later announced a $600 million external funding round to advance its AI drug design engine. This is important because it shows the market is willing to assign very large economic value to AI systems that change scientific workflows, not just office workflows. That is the deeper point. Language models mostly help humans process information faster. Scientific foundation models can alter the search space itself. They can point researchers towards structures, interactions, and hypotheses that would have taken much longer to uncover using conventional pipelines. If you shorten drug discovery cycles, improve hit identification, and reduce failed experiments, the value created is measured in years and billions. So when people say AI is mostly hype, this is one of the strongest counterexamples. In science, we already have a category where AI changed what researchers can do. Section 7. Neurosymbolic and verifier-based reasoning. When next word prediction stops being enough. The seventh breakthrough is hybrid reasoning. This is the idea that some hard problems may require more than next token prediction. They may require combinations of neural models with search, verification, formal reasoning, or symbolic structure. DeepMind's alpha geometry was an early signal. The company said alpha geometry solved 25 out of 30 Olympiad geometry problems in a benchmark, compared with 10 for the previous state-of-the-art. Then DeepMind said Alpha Geometry 2 could solve 83% of historical IMO geometry problems from the past 25 years. At IMO 2024, DeepMind says Alpha Geometry 2 and Alpha Proof together achieved silver medal standard by solving 4 out of 6 problems. Why is that disruptive? Because it suggests that some of the next major gains in AI may come from architecture, not just scale. A giant language model can sound fluent and still fail on tasks that demand strict correctness. A hybrid system with search, structure, and verification may be less flashy in conversation, but much more powerful where the answer has to be exactly right. And those domains are everywhere. Mathematics, code verification, formal proofs, scientific reasoning, engineering, compliance, and safety-critical workflows. So the lesson from alpha geometry and alpha proof is not just that AI got better at math. The deeper lesson is that the future may involve hybrid stacks, neural generation, external tools, formal verifiers, structured representations, and search. That is a very different picture from the early chatbot era. The field is not abandoning language models. It is surrounding them with new machinery. Section 8. The Silicon Ceiling. For the last decade, AI progress has looked like a straight line pointing up. Bigger models, more data, more compute, more capability. But if you look closer at the engineering, we are not flying. We are climbing a ladder, and we are getting close to the ceiling. I call this the silicon ceiling. It is the point where brute force scaling starts colliding with hard limits in memory, power, and economics. For years, the dominant logic of AI was simple. If the model gets better when you scale it, then keep scaling it. More parameters, more training tokens, more GPUs. And that strategy worked. But now, the hardware is no longer just the engine of progress. It is becoming the constraint. There are 3 layers to the ceiling that every founder, engineer, and investor needs to understand. 1. The memory wall. Transformer systems do not only need compute, they need memory bandwidth. And at long context lengths, that becomes brutal. As prompts grow, the KV cache grows with them. That cache is basically the model's short-term working memory during inference. And the problem is not theoretical anymore. NVIDIA explicitly describes KV cache as a bottleneck for LLM inference, because GPU memory is limited and costly, and the cache grows as prompts get longer and multi-turn sessions stay alive. NVIDIA's own optimization posts now focus heavily on reducing KV cache pressure, which tells you the bottleneck is real enough to shape product design. So the challenge is no longer only, can the model think? It is, can the hardware afford to remember what it was thinking? This is where newer architectures start to matter. Take Mamba, one of the most important post-transformer sequence model papers in recent years. Mamba is built on selective state space models, or SSMs. In plain English, a transformer tries to look at a lot of the sequence at once, comparing many tokens to many others. Mamba works differently. It keeps a flowing internal state and updates it as information arrives. So instead of repeatedly rereading the whole notebook, it tries to carry forward the right summary. That matters because it changes the scaling behavior. The original Mamba paper says the model has linear scaling in sequence length, around 5 times higher throughput than transformers in the reported setup, and improved performance on real data up to million-length sequences. That does not mean transformers disappear. But it does mean the field is seriously looking for architectures that can escape the memory behavior of brute force attention. In simple terms, Mamba is not trying to build a bigger transformer. It is trying to build a more memory-efficient sequence engine. 2. The power wall. The second limit is power. At frontier scale, AI is no longer just a software problem. It is an infrastructure problem. The U.S. Department of Energy says AI and machine learning require tremendous amounts of stable electricity generation and cites estimates that data centers could consume up to 12% of total U.S. energy production in 2028. DOE also released a report saying data center load growth has tripled over the past decade and is projected to double or triple again by 2028. That is extraordinary. It means scaling AI is starting to look less like app development and more like industrial planning. This is why the industry is now obsessed with data center siting, cooling, substations, dedicated power, and in some cases, nuclear-adjacent energy strategies. So when people talk about scaling a model, they are often really talking about scaling an energy system. And this is where the phrase, just add more GPUs, starts to break down. Because once compute demand starts pushing against grid constraints, the bottleneck moves outside the chip. It becomes a civil engineering problem. a power delivery problem, a capital expenditure problem, and that is a very different kind of ceiling. 3. The economic wall. Then there is the third limit, cost. At frontier scale, brute force scaling becomes economically dangerous. Sam Altman said training GPT-4 cost more than $100 million. Even if the exact figure varies by accounting method, the broader point is clear. At the frontier, one training cycle is no longer just a research experiment. It is a major capital allocation decision. And when the cost curve rises faster than the return curve, the alpha starts to disappear. At that point, better architecture matters more than brute force spending. That is why some of the most interesting work in AI right now is not about making the biggest model. It is about making the smartest system per watt, per dollar, and per gigabyte. So what breaks the ceiling? Not one thing. Probably a stack of architectural shifts. And 3 of the most important are already visible. First, state space models, including Mamba. State space models matter because they attack the sequence problem differently. They are built to process long streams efficiently, with recurrence and compressed state, rather than full quadratic attention over every token. That makes them one of the clearest examples of the field searching for post-transformer sequence backbones. Mamba is important not because it wins every benchmark forever. It is important because it proves a serious point. There are credible alternatives to pure attention scaling. Second, liquid AI and hybrid dynamical architectures. Liquid AI is interesting because it is trying to rethink efficiency from the ground up. The company says its liquid foundation models were built around smaller memory footprints and efficient inference across CPUs, GPUs, and NPUs. It later released LFM 2.5-1.2b-thinking and said the model runs entirely on device, fits within 900 megabytes of memory on a phone, and is optimized for on-device reasoning. Why does that matter? Because it points to a different future. Not one giant cloud brain, but many smaller, faster, deployable systems. That is not just a model story. It is a distribution story. If intelligence becomes fast, private, and local, then some of the value shifts away from giant centralized clusters and back toward devices, vehicles, edge systems, and embedded products. That is one way to lower dependence on brute force centralized compute. Third, neuromorphic chips. This is where the story gets even more radical. Neuromorphic hardware is based on a very different idea from standard GPU-style computation. Instead of constant, dense, clock-driven processing, neuromorphic systems use sparse, event-driven computation, inspired by spiking neural systems. Intel's Loihi 2 is one of the clearest real-world examples. Intel says Loihi 2 focuses on sparse, event-driven computation that minimizes activity and data movement, and says research using Loihi 2 has shown orders of magnitude gains in efficiency, speed, and adaptability on small-scale edge workloads. Intel's technical brief also says Loihi 2 delivered up to 10 times faster spike generation than its predecessor, and Intel's HoloPoint announcement said Loihi-based systems can reach 100 times less energy and speeds as much as 50 times faster than conventional CPU and GPU architectures on some optimization and inference workloads. That last part matters, because one of the deepest problems in current AI hardware is that moving data is expensive. Neuromorphic designs try to reduce that movement by changing the computation model itself. In other words, instead of trying to push today's architecture harder, they change the architecture. And that is exactly the kind of shift that can break a ceiling. A simple note on quantum computing. When people hear the phrase quantum leap, they often imagine a magic computer that does everything today's GPUs do, only much faster. That is not the right mental model. In layman's terms, a transformer is like a giant room full of clerks comparing words, sentence by sentence, and passing notes back and forth. A quantum computer is a very different type of machine, built for certain specialized classes of problems, especially ones tied to quantum physics, chemistry, and some optimization patterns. IBM explicitly says quantum computing is not expected to fully replace classical computing, and that quantum and classical systems are expected to work together in combined workflows. IBM also notes that classical systems remain faster and more reliable for many tasks today. So when I say we need a quantum leap, I do not mean tomorrow's chatbot just moves from GPUs onto a quantum box. I mean, we need a jump in architecture, a change in the way intelligence is computed. The same way the transistor did not simply make the vacuum tube bigger. It replaced the paradigm. And that is the real point of the silicon ceiling. We're at a crossroads where simply scaling the old pattern may no longer be enough. The next leap in AI will probably come from escaping the current bottlenecks. Memory bottlenecks, power bottlenecks, economic bottlenecks, and eventually architectural bottlenecks. We need to stop trying to build a bigger ladder and start building a rocket. If you step back, a pattern becomes obvious. The AI industry is moving in several directions at once. Toward multimodal systems that can perceive, toward agents that can act, toward world models that can simulate, toward small models that can run locally, toward privacy-preserving learning that can scale under real constraints, toward scientific models that can accelerate discovery, toward hybrid reasoning systems that can verify, not just generate, and toward entirely new architectures that may break the current silicon bottlenecks. That is why the next wave of AI disruption will not look like the last one. The chatbot was only the opening act. What comes next is a stack of technologies that expand AI from language into action, science, hardware, privacy, and the physical world. And the most important point is this: none of these categories are purely speculative. They already have real deployments, real benchmarks, or real commercial signals behind them. That does not mean every company will win. It does not mean every demo will turn into a product. But it does mean the frontier has already moved. So the smartest way to think about AI now is not to ask whether LLMs are overhyped or underhyped. It is to ask which capabilities beyond LLMs will matter most when AI stops being just software you talk to and becomes infrastructure that sees, acts, verifies, discovers, and eventually computes in new ways. That is the real race. And that is where the next breakthroughs are coming from.